Okay, yeah. So welcome to lecture 23, and today we are going to start with Copula. So I know it's really a word that means nothing to you guys as of now, but I'm hoping that as in when we, I'm hoping to complete this chapter in 3 classes. And I guess it's a fairly easy chapter and a bit like the extreme value theory that we studied. So it might involve some notations which might seem a bit complex, but they are relatively simple, and the intuition is the main thing that will keep you guys grounded in this particular topic at least. Yeah. So I guess what happens is whenever we want to measure dependency, so again, Copula is something which will be used to measure dependency. But again, first, I guess we should have a look at the kind of measures of dependency that you guys have yet studied. So do you guys remember anything that you used to, use in terms of statistical methods to figure out the correlation, causation, or the association between two random variables from what you guys studied in CS1? Anyone? Has anyone heard of rho? So I guess generally you might have heard of this rho here, or something like rank correlation coefficient. Yes or no? Did you guys study this in CS1?
Yes, ma'am.
Yes, right. So, I mean, are you guys, I don't know why are you guys so quiet today, but yeah, just try to respond if you can, but it's all right. So again, there are some different measures in statistics that you can use to try and measure, the dependence between two variables. And if at all there exists any correlation, or if at all there is any dependency between the two variables that you are concerned about. So let us say that, the first thing that you might have studied was Pearson's linear coefficient. So it's basically Pearson's rho as well. And again, the very fact that it states linear here. So if you take something like this, for example, so let's say you have y equal to x squared, and you try to plot the correlation between y and x, you might get something around 0, even though you know that there is some dependency here. But again, because this coefficient only tells you information about the linear dependency, and this x squared being non-linear wouldn't be captured along in this value of rho here. So that is one of the disadvantages, but again, it is quite helpful and very simple when you only have to take into consideration the linear correlations. So this is used for linear correlation coefficient. So this is, let's say, your first method, and the very simple formula for this is you just take covariance of, let's say, x comma y, if these two are the variables that you care about, and you normalize them using these standard deviations. So when I'm taking square root of variance, it essentially is just, dividing these covariance by the standard deviation to normalize them. And again, this is going to be thus a unit-free quantity. So this is just going to be a number between -1 to 1. So this will belong to -1 and 1, right? It cannot exceed 1 and it cannot go below -1. So let us say if I say that, my rho is 1, or let us start with 0. So if I say my rho is 0, what does it mean? Anyone?
There is no correlation between x and y.
Okay, so there is no linear correlation between x and y, right?
Yes.
Okay, so now if I tell you guys that my rho is 1, then what does it mean?
Positive correlation.
Positive correlation, exactly. Positive. Yeah, and yes, it is perfect positive correlation because it is precisely 1, not only a positive number, but also 1. So we know that it is perfectly positively correlated, that if I see an increase in x, then I'm I will definitely see an increase in y as well. Okay, so that's there. And then if you have -1, it's just the opposite. So if there's an increase in x, there will be similar decrease in y. So I guess that's clear with everyone. But again, there are some sort of, cons to using this type of measure to try and, basically see if there's any correlation. So the very first thing is also the fact that, if you transform this variable, so let us say now we were looking at the correlation between x and y, okay? But now if let's say you have to look at the correlation between e raised to x and e raised to y. So again, if I increase my x, if my y also increases, then what would you expect? You would expect that if you increase your e raised to x, then your e raised to y should also increase. But again, the nature of increase is not the same. So what happens with Pearson's linear correlation coefficient is that only if you apply a linear transformation on these variables x and y, this row will remain same. But if you apply some non-linear, or let's say even if you apply strictly increasing transformation, which is something like e here or log or anything else, you wouldn't get the same value of rho, which might seem very counterintuitive, right? Because here you see that if you increase your x, your y should also, and if you increase your x, your y also increases, then this increase should also lead to an increase in this. And again, we aren't only talking about the increase, we are also talking about the nature of increase, the amount of increase, because we have a specific number which will measure the exact kind of relationship that there is between x and y, okay? But again, we also have to be aware that, this only tells us something about the correlation. And again, as we know, if at all I say that the correlation between x and y is 0, that does not always imply that x and y are independent as well. And the very simple example is this right here again. So again here, if I'm looking at y equals to x squared, I would say that the linear correlation, and we often call it correlation because always we're looking at linear at least in this subject here. So the correlation here is going to be 0. But we see that y and x are not necessarily independent. So there are certain other things that these x and y will have to satisfy for them to be independent, and we'll have a look at that with an example as well. But for now, I guess you guys do know that, if and only if you know that these two variables are independent, then you can say that for sure the correlation between them is 0. But if you only know that the correlation between them is 0, you cannot for sure say whether your x and y are independent or dependent variables. So this is usually termed as, correlation does not imply causation. And I guess this nerd Halloween parties, people do wear t-shirts, saying these quotes. And you also see memes, I guess, around usually stating that correlation does not imply causation. So you have to be aware of the kind of inferences that you draw from the statistical methods that you have applied. And I guess this is just, very crucial to understand what a particular measure allows you to do and what it does not allow you to do, so as to not, misuse it and conclude some wrong findings, which might not, hold true otherwise. So that's one thing. But again, what happens here is, let us say if I give you guys some marginal distributions. So let us say I tell you guys that, I have one distribution. Let us say I have a joint distribution of x and y, which follows bivariate normal distribution, basically bivariate Gaussian distribution. So I'm saying bivariate because there are two variables, x and y here. So if I say that my x, y combinedly, so basically what I'm saying is, I'm talking about fxy here, okay? If my xy here follows a bivariate Gaussian distribution, then my question is to all of you, will my x and y follow univariate normal distribution? So I'm saying that if this is a bivariate Gaussian distribution, Gaussian and normal are just, interchangeably used. So if I'm saying that my f of xy is a bivariate Gaussian distribution, then can I conclude on the basis of this information only that my x is a univariate Gaussian and my y will also be a univariate Gaussian distribution? Yes or no? What do you guys think? Anyone? So what I asked was, let's say if I give you guys a random variable x, y, and if I tell you that my x, y together follows a normal distribution, then can you conclude on the basis of that information whether my x and y will separately also follow normal distribution? Anyone has any idea about this? Yes or no? Or would you just want to guess? What do you guys think the answer will be? Am I audible? Hello.
Yes, ma'am.
Okay, yeah. Okay, all right. So at least if you don't know, you can see me, that, okay, we aren't sure or something of that nature, so that I understand at least whether you guys are thinking about it or what else.
Ma'am, so f of xy, as in wherever there is just x usually, there will be x plus y or just x into y.
X plus Y. I mean,
Okay.
not precisely even X plus Y, I would say, but it could be any combination of X and Y.
Then probably we can't say that, ma'am, that x and y will follow separate
And
univariate normal distributions.
okay, okay. Why do you think so? And what about others? Do you guys agree with what Isha just said? Yes.
Ma'am, honestly, I don't have any idea.
Okay, okay. No worries. What about others?
Ma'am, I think individual distribution won't follow normal.
Individual distributions won't follow normal. So, okay, what happens is, let us say if I ask you another question. So now this is a reverse question. If I give you guys X, which is a normal distribution, and if I give you guys a Y, which is also a normal distribution, then what will be the distribution of XY? What do you think? Will that be normal again, or will that not be normal?
Are we assuming that X and Y's are independent or anything like that?
No, so I haven't necessarily said that, and I don't know if they are independent or not. So, okay, let me just, break it out for now. What happens is usually, let us say if I give you guys a bivariate Gaussian XY, then I can always say, because of the independence property, that my X will follow normal and my Y will follow normal separately as well. I mean, that is true in any case for any bivariate Gaussian distribution or even multivariate Gaussian distribution. But again, if you're looking at X1, let's say if you're looking at X and Y separately, then you won't be able to necessarily tell whether your XY will be a bivariate Gaussian or not. And again, the very first thing that you can also say, because this XY is bivariate, that your X will also be normal and Y will also be normal, is only in the case of normal, not in the case of any other distribution. So there is some issue that we have in modeling the joint distribution and maybe connecting or maybe deriving the marginal distributions from those known joint distributions. And this is something where Copula will, help us. So Copula will help us to couple together two marginal PDFs of some distribution. So they need not be normal. They can be, one can be beta and one can be Gumbel. One can be other distribution and the other can be a whole another family of distribution as well. So Copula, irrespective of the families that these individual marginal distributions come from, Copula will help us to couple them together to give us one particular CDF for those variables combined. So basically it will give us a joint CDF of these variables. And again, we'll have a look at how that happens and how does even Copula look like. I'll show you guys some pictures in the next class. But today we will have a look at some graphs. And I guess even before we do that, let us have a look at the another kind of measure of dependency that we generally study. So I guess you guys must have studied also about, rank correlations. So in rank correlations, what happens is, okay, maybe if I just write a particular formula. So there are many different methods again, which depend on the rank of the numbers, not exactly the amount of the numbers, but rank of the numbers. So let's say if you do some strictly increasing transformation on those numbers, their ranks will not change, right? So this measure will remain the same. Even if you do a linear transformation or a non-linear transformation or a increasing transformation on the random variables that you are trying to figure out the association between, right? So that property is known as invariance property. So we can say that the measures which use rank correlation are invariant to the transformations on the random variables. And again, one of the examples is Spearman's rho. So I'm just going to write Spearman's rho here. And its formula is something like this. I'm just going to write it from the book itself. And then you sum up for di squared, where I go from 1 to t. Now, what is t here? T is the number of observations that you see. So it will be the pair of observations here. And di will be the difference in the rank for the ith observation part. And this is the thing that's going to make this rho invariant, because this di will not differ if you do any transformations on the x or y random variable, which is increasing, non-linear or linear, right? And that is one of the advantages of using rank correlation over Pearson's linear correlation coefficient. And again, there is another type of rank correlation, which is Kendall tau, which looks at a difference between, the number of pairs that go together and the number of pairs that go opposite. And then you divide it to normalize again. But you don't necessarily have to get into the nitty-gritties of how these rank correlations work. But you also need to know that this is one of the ways to model these joint distributions, because it will hedge against, the transformation of the random variables that you do. And now if I say that my x and y are independent, then this rank correlation is going to be 0 for sure. Again, similar to the way it was in Pearson's. And if I say that my x and y are co-monotonic, basically the situation where you would have had a 1 here, then here also this Spearman's rule will take the value of 1. And it will be -1 if they are counter monotonic. So whenever I'm saying monotonic transformation, what does come to your mind first? I guess we studied, why do we use log when we use the method of maximum likelihood? Because it is a strictly monotonic increasing function, right, of x. And as in when you increase the x, your f of x also increases, where your f of x is just log of x, with the example that we are talking about now. And I think that's it. And that is something about, the rank correlation coefficients. And what do these measures do? These measures will measure the dependency. They will measure the correlation that there is between these two random variables. But again, let me give you guys an example of why do we need to care about these correlations between, let's say, x and y. Okay, so let us say there is a landlord. Let us say Mihir has, given out some money as a loan to Isha and to Anvaya. Okay, so let me just plot something. So I'm gonna plot on x-axis the money that has been repaid by Isha. Okay, so a repayment by Isha. And on the y-axis, I'm gonna plot repayment by Anvaya. Okay, so this is my x-axis and this is my y-axis. So now what Mihir will have to be concerned about is the case where both of these guys do not pay him the money back, because that will be the worrisome case for him. So again, maybe I can choose to define this one universe in 4 different categories. So maybe what I can do is I will just draw a line here and I will draw another line there. Okay. So now what's happening is, and let us say, so this is the amount which Isha will pay. So let us say, for now, let me just say that, this much amount has been lended to Isha and this much amount has been lended to Anvaya. So this is the total that these guys will have to pay to Mihir, okay? And let us say if there's a point here, I can just see that this is x and this is y, where x represents the total amount lent to Isha and y represents the total amount lent to Anvaya, okay? So what I'm going to do now is try and specify these 4 quadrants. So let us say if Isha pays the money. So again, I have just, not deliberately drawn this line here so as to, just specify something that I'll tell you in a minute, let's say. Okay, so let us say Isha repays the money and Anvaya also repays the money. So we are in this quadrant, okay, where both repay. So this is the quadrant which specifies where both of them will repay the money to Mihir, okay. But now what happens, let us say if Isha has paid the money but Anvaya defaults. So what happens is you will be here. So all the coordinates in here represent the case where Isha pays and Anvaya defaults. Okay, so these green are the cases where Isha has paid the money back because it is some higher number, but for Anvaya on y-axis you can see it is only from 0 till here. So it's likely that Anvaya has defaulted, and the opposite would be the case here. So here would be the case where Anvaya has paid and Isha has basically defaulted on the loan. Okay, But the most worry for me here would be the case where Isha doesn't pay and Anvaya doesn't pay as well, which is this area right here. And sometimes you do not necessarily care, like in the case of extreme value theory, about the whole distribution. You only care about this little quadrant right here. You only care about this lower tail here, that what happens and what are the chances that neither Isha nor Anvaya will repay him his money back. So this is the case where both default. Okay, and this is the case that we will try to look at now using tail dependency. So the kind of dependency measures that you guys have studied up until now in CS1 were something like this. So you studied about Pearson, you studied about rank correlations, but there is third measure of dependency that is of utmost importance, especially in risk management sectors, when it comes to measuring the tail dependency. So this is in general known as tail dependence. So I'm just going to write tail dependence. And we'll have a look of methods which will help us to measure this tail dependence. And Copula is one of those functions. So Copula is a function actually. It is like a CDF, which will help you to couple things together and figure out things easily in a better manner than it would have been otherwise. And it actually comes from a Latin word which means to join together. So it does make much more sense as well. So I guess now that we know what we care the most about, which is this little quadrant, we have to look at the methods and we have to devise some methods which will help us, figure out the probability over here. So again, whenever I'm talking about probability that Isha will default and the probability that Anvaya will default, if I want to figure out this, let me just write it maybe. So probability that Isha defaults and Anvaya defaults. What do you guys think this will be? So let me just say that, the probability that Isha defaults is 0.05 and the probability that Anvaya defaults is 0.1. Then what do you guys think will be the probability that both Isha and Anvaya defaults? Anyone?
It would be the multiplication of the individual probabilities.
Okay, so you say that it would be the multiple of the individual probabilities. Okay, what about others? What do others think of this?
Yes, ma'am. Same. It will be multiplication of probability that Isha defaults and probability that Anvaya defaults.
And what about the rest of you guys? Do you guys also think the same? Do you guys agree with what they are?
Yes, ma'am. Since they are independent.
Yeah, if they're independent, then
yeah. So we have to assume that they are independent, right? And only then we can multiply. Only if these events are independent. So again, let me give you guys one example now. Let us say that both Isha and Anvaya work in a firm which has now suffered huge losses, and now they are trying to lay off people. Okay, and the very fact that Anvaya defaulted was because she was one of those persons who got actually laid off by the company. And Anvaya and Isha, don't take this example personally. I really hope you guys don't get laid off anytime. But again, this is just an example of you. So let us say the company fires Anvaya. Then does the chances of Isha also defaulting on the loan increase, decrease, or remain same? What do you guys think? If both of them work in the same department at the same level and at the same position and everything else. What do you guys think?
I think it will increase.
Yes, ma'am, increase.
It will increase, right? So again, Mihir does not necessarily have to concern himself about whether Isha and Anvaya individually default. He also have to take into consideration the chance that is there any implicit dependency among Anvaya and Isha which would render, if at all one defaults, the other guy also defaulting. And that is what we care about. And that won't be this right here, right? So if let's say Anvaya defaults somehow, then the chance that Isha will default won't be 0.05 anymore. It will increase a lot. And again, you can take another maybe very intuitive another example for this. It could just be, the case where let's say you have a manufacturing firm and they derive their raw materials from some another individual corporation. Okay. And let us say that individual corporation goes bust and they are now in a financially dire situation and they aren't able to supply those raw materials to the manufacturing firm. Then the rate of default of the manufacturing firm will also increase higher than it would have been in the normal cases when the individual corporation didn't really default. So Copula will come in handy. Again, not all Copulas will come in handy. And this was actually one of the reasons. And one of the reasons why there was, the whole financial crisis of 2007-8. And there was a copula known as Gaussian copula invented by a person called Lee. And he had a scientific paper specifying precisely the assumptions that the copula rested upon, which was independence. One of those assumptions was that, these risks are independent of each other. And people in finance industry ignore that assumption, or maybe didn't really weigh into that assumption, thinking that it really doesn't matter, or it's very highly improbable sort of something. And that is what led to the underestimation of the risks that they thought they had. So there is a term known as value at risk, which helps you to identify how much of your firm's value is at risk at a particular point in time. So in the worst case scenario, what is the worst loss that your company could, handle? And what happened was these estimates of the worst possible loss to a particular company was underestimated because they assumed that the risks that they had were independent, wherein in actuality they were not. And what happened was they never really thought, that these credit rating agencies would in any way be connected to the defaults in the housing sector. And that is what happened. And I guess if you might have seen the movie The Big Short, wherein they precisely explain, why the credit default options and how they were priced. So this copula is something which is used to price this financial exotic options, and one of those went really wrong and everyone was using it somehow, not really, taking into consideration the assumption that the theory was built upon, and it led to the crisis that we all know about, basically. So sometimes we take very, lightly this theory that we study, but again, it is of utmost crucial importance to even, understand what assumptions a particular theory relies upon. And that will only help you maybe not to, basically avoid the risk, but it will at least help you to measure the risk as accurately as possible so as to hedge against it and reserve against it. And Copula is just something that you can use to price these financial derivatives, financial options accurately. And again, within this subject, we don't necessarily go into the applications of copulas because that's certainly, copula is one of the graduate level topics. And this again wasn't included in the CT6 when I studied. So now the very fact that it is included is a very nice thing, I would say. And again, this is one of the topics which is of very importance in risk management in terms of understanding the theoretical part as well, I would say. And not always you will use copula because these can be complex, and if you don't understand them well, then you better not use it to price your securities, because you don't know the underlying risks that there are of, even using Copula to price risk. So I guess that was maybe, a way much more critical analysis or a caveat, I would say, just, before even telling you guys what Copula is. So I'm not trying to scare you guys off, but again, we have to be aware, and it is really important. So again, now that we all know what we should be careful about and everything, let us try to see through the lens of what we have yet studied and understand what Copula actually is and what does it even help us to do. And why do we even need a Copula in the first place? Okay, why can't we do just with the joint distributions and the marginal distributions that we have? So maybe let me just pull up the book here. And there is a nice example that we can go through. It's the page number, this is something around. Okay, so I guess you all must have already studied, what is a joint distribution, what is a density function. I mean, density function is just the PDF, and joint distribution is something like this. So f of x y, where you are in a way calculating the probability that you observe not only x less than or equal to x, but also y less than or equal to y simultaneously to this observation. And again, this was the bivariate case that I was talking about, but only for normal. So x, y were normal, but again, now here you can actually extend it to the multivariate case as well, where you have d number of x's, not only x and y, but x1, x2, and up until xd. And again, if you want to figure out using the PDF of f of xy, the CDF, what you have to do is, because you have two variables, you integrate it twice, once over x and once over y values. And let us go through an example, I guess. I'm just gonna skip this because we all will just learn it using an example. I guess this is just going to be a refresher for you guys, because this you must have already studied previously. Okay, so if I mean, we just solve this question first, I would say, and then we'll get the idea of where Copula comes in the picture here. So let us say we have a joint PDF for two continuous random variables. So again, remember, we're looking at only continuous random variables, and during this whole chapter, we will never look at discrete distributions per se, because the Copula theory, when you have discrete distributions, is way much more complex than if we have continuous distributions. But again, it's good that in finance we look at continuous random variables, at least for this chapter. So we have f of xy taking this particular value, and remember, our x takes only values from 0 to 2, and my y also takes values between 0 and 2 only. So now they have asked us to derive a formula for the joint CDF, which is denoted by capital F of xy, as we would have expected. So again, what we have here is this. So I'm hoping that all of you know how to write this small f in terms of, how to write this capital F in terms of small f. So again, usually when we are looking only at one particular variable, which is, let's say, x, what you do is you integrate it from 0 to x, f of x dx, right? So now if you have x comma y, what you're going to do is, so this s and t is, okay, yeah, so again here it won't be x. We can just, say that this is some x prime, and this x prime and this s and t are just placeholder values for x and y. So ultimately, when you integrate this, you will get some value, some answer, which will be in terms of x and y. And again, these are not the random variables. These are the values that the random variables will take. So this x corresponds to this and this y corresponds to this y, not the capital X and Y. Okay. And this S and T is just, again, the values here. And because you are writing this f of st, S for the x and t for the y, you replace f of xy with f of st by replacing x with s and y with t here. And you get this thing. And then you just do your normal integration stuff here. And the answer that you will get is the joint CDF of x and y. So this here represents the probability that you will observe the value of capital X random variable less than or equal to small x, along with the capital random variable y's value being no greater than this small y. Okay, and that's it about deriving the joint CDF using the joint marginal. So remember, you knew the joint PDF and you just had to integrate and you got your joint CDF. Okay. Let us see what the second question asks us of now. So now that we know the joint CDF, the joint PDF, we are asked to derive a formula for the marginal PDF, f of x and f of y separately, and comment if these are independent. So again, does anyone know what is the criteria that x and y should satisfy for these guys to be independent in terms of probability?
If the marginal probability product is equal to the PDF of joint, then it is independent.
Exactly right. So if we multiply all the marginals, basically here if you multiply f of x and f of y, we should ideally get what we derived here, which is the joint CDF, right? Which is capital F of xy. Oh no, sorry, we should get this joint PDF. So if we multiply this small f, small y, we should get small f xy, right? And let us see if that happens. But again, prior to doing that, we have to figure out what is f of x and what is f of y. So does anyone know what should I be doing here?
For f of x,
Integrate over the limits of x and y respectively. So for y, we will integrate it over x.
Yeah, exactly. So this is very important, and yeah, correctly said. So what we will have to do is, for figuring out the f of x, you will integrate it over the limits of y. So what you're doing is essentially you're substituting in checking it for all the values of y, what are the values that your x will take, and simultaneously you get the chances of observing each of these x's, and you just integrate it over y and you remove these y values because you're substituting 0 to 2, and at the end you only end up something having x random variable, not any of y in there, and that is what is your f of x. So now to figure out the marginal PDF of y, you will do the same thing but integrate over x value and you get something like this. And now again, if you try to multiply this with this, you can clearly see that you get something like 1 upon 100, and this is clearly not at all equal to this here, right? And which is why these guys are really not independent of each other. So that is what they see here as well. We therefore deduce that x and y are not independent. Okay, so I guess that is good. But now let us see what do they ask us of again. Now they're asking us to derive the formula for the marginal CDFs, f of x and f of y. And I guess this is fairly simple because you only have one random variable, and what you will have to do is just integrate it over 0 to x, s ds, and here 0 to y, t dt. And if you do the integration, you will get something like this and something like this. This is the PDF of x and this is the PDF of y. So f of x and f of y here. Is this clear to everyone? I guess this was just like a recap. But again, now if I tell you guys that I have to figure out, the nature of association between this x and this y using only the marginals that I have. So let us say I know f of x, let me write. Let us say I know small f of x and I know small f of y, okay? And I know the nature of association, the nature of dependency between these. And I also know the dependence structure. So the way they depend on each other, I know that. So can these three help me to figure out a joint CDF for these guys using the method that I have just used? So what happens is, the very first time when we integrated it twice to determine the joint CDF, that itself will not be able to tell you anything about the association that there is between the X variable and the Y variable. So this whole chapter is going to be about, how copula comes in handy when we have to determine the nature of association between these random variables. And again, I mean, it's fairly simple, and again, it's kind of magic, I would say, how it connects the marginals and the CDFs. So the very, when I studied this topic, it was actually during a summer school, for which I was granted a scholarship to study at the London School of Economics. And there was a professor who was working in JP Morgan during the financial crisis. And he was the one who taught me. And he actually drew a really nice diagram, which I'm going to draw it for you guys now, which will make it really clear, I guess, how you can derive marginals from the CDFs and how you can derive this joint CDFs by only knowing the marginals. So what we did now was, we knew the joint PDF, right? And we used that PDF and we integrated it to figure out the marginals. But if we know the marginal, is there a way to figure out the joint? That is what is the question here, and that is what we will try to answer. But again, before we get to that really nice diagram that my professor drew, let me make you guys understand another concept. So let us say if I draw something here, okay? This is my X here, and here I'm drawing f of X. So this is normally how a PDF would look like, and it will never decrease, can increase, and let's say that is 1. Okay, so if I have some X here, and so again, this line, this curve that I have drawn here is f dot, right? So whatever my X value is, it will apply f to it and give me corresponding f of X value, right? And let's say if I know my f of X, I can apply f inverse to it to come back to my value of X. Okay, so let me just, now we'll see this thing mathematically, and we will try to figure out the distribution of this CDF. So remind me once again, you guys, what are the limits on the values that this CDF can take? Anyone? CDF can take only values between? Are you guys there? So by CDF, I mean capital F of X. What is the bound on F of X? I don't think it should even take this long for you guys to answer this question.
There is no bound, right, ma'am?
Why? Can
like for
can these...
PDF it should be 0 to 1, but for CDF we don't really know, right?
Does everyone agree with what Isha just said? So okay, for normal, my PDF is something like this, right? And my CDF is again going to look something like this, right? This is for the normal case. And my CDF, we know what is CDF. So my CDF is just f of X, which measures the probability that my X random variable will take a value less than or equal to X. And what is my small f of X? It is something 1 upon blah, 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 integration e raised to blah, 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 right? So what are the values that a probability can take? It can only be between 0 and 1, right? And so can my f of x be?
No, that's
Do you guys remember this? So whenever I'm talking about this CDF, it can only take values between 0 and 1. Never beyond this and never beyond that. And whenever I'm talking about PDF, it can essentially take values from minus infinity till infinity. Does this make sense to everyone? Are you guys still confused about this? Yes. So again, can someone remind me what are the bounds on my values that this CDF can take? Are you guys there?
Yes, ma'am.
Yeah. So is this clear to everyone? Yes or no? At least you can respond, I feel.
Yes, ma'am.
Okay, thank you, Mir. What about others?
yes, ma'am.
Okay, thank you, Savri. Isha, do you understand? Were you confused between PDF and CDF? So PDF is something that we denote as, small f of x. And CDF is something which is capital F of x, which is a measure of probability that you will observe, this capital X less than or equal to small x. So the area under this curve sums up to 1. But the thing on the y-axis over here can only go up until 1.
Got it, ma'am. Because in CDF also we are considering sort of like a probability only. So it should be under 1 itself.
Yeah, so remember when I discussed the difference between probability and likelihood. There is one thing that goes under the curve and there is one thing that is measured on the y-axis. And I guess that is what this is about. But again, so I mean, you should so now I guess this is clear to you guys that capital F of x can only take values between 0 and 1. It can never exceed 1 and it can never go beyond 0. Because again, probability can never be negative and this thing cannot exceed 1 as well, probability. So, okay, that's it. So now I can easily write that my f of x is nothing but the probability that x takes a value less than or equal to x. But remember, what did I promise you guys? I said that we will figure out a distribution for this f of x here. Now you probably might be wondering that this f of x is just a constant. So how can I, basically figure out its distribution? So again, we are assuming that we do not know the value of this x, and that is why you are still defining it in terms of this. And now what I'm going to do is, I'm just going to define this f of x as u. So this u is my random variable, which now takes values only between 0 and 1. But I have to figure out what distribution it follows, and will come to a conclusion that it follows a uniform distribution. And I'll tell you guys why does it follow a uniform distribution. There is such a nice explanation, but again, let us go to the math first as well. So again, what I can write is, this is a small x, the value that my capital X variable takes. So if I'm writing f of x here, I can write that, so remember, if I'm talking about u, what will I write? I'll write that my u takes a value less than or equal to small u, right? So this f of x, which is the random variable capital U, will take the value small u, right? And now if I apply F inverse on the right hand side as well as the left hand side, what do I get? So I do F inverse F of X here, and I do F inverse of U here. So what do I have here? F inverse and F would cancel and I'll be left with X. And what I have here is F inverse of U. So remember, this is exactly like this. So this F of X is equal to small u here. And again, I'm just applying F inverse transformation on U to come back to my value that I started off with. So remember, I can rewrite my X as F inverse of U. And it is looking at the nature of relationship that transforms U using a function F inverse to get you to X here. Okay. So now what I'm going to do is, I'm just going to substitute this X value up here again. So I take this here and instead of X, I'm going to write this F inverse of U. And that will be equal to small u again here. Does this make sense to everyone? And again, just to remind ourselves, this F is with respect to random variable X, okay? Not U. So this F is with respect to X. So again, now that we have this, what can I write this as? So I will observe that if I have anything in bracket with F of X, which is something like this, I can rewrite it as this, where this X is just this X. So I'm going to rewrite this thing as, so instead of F of X, I'm going to use this probability that my X takes a value less than or equal to this small x is the thing that's there in the brackets, which is everything right here. So my X less than or equal to Fx inverse of U, and this is equal to small u here, right? So remember, this thing right here is what you have in the brackets here, okay? And now if I were to just, do the calculations again, what I'm going to do is just take this F inverse and put it back here as F of X. So this will be less than or equal to U, and that gives me the value of U. So do you see how instead of a random variable, now I have a F of X here, right? So remember, when I talk about probability that X is less than or equal to small x, what is my random variable? This right here. And now I have in a way derived the CDF of F of X. Do you guys see the beauty of it? I mean, I have basically done substitution, resubstitution within itself to get to a point. I mean, I do not expect you guys to even remember these steps. Probably do not even need to, basically do this any time in the exam. But this is just how you derive the fact that your F of X is indeed a uniform distribution. Because what is this telling you? This tells you that the chance that you will observe a F of X which is less than or equal to U is just equal to U. And this is a property of the uniform distribution, right? So what you have in uniform distribution anytime, and again here this holds true. Why? Because again you're looking at uniform between 0 and 1. So on the y-axis as well, you only have 0 to 1. So for anything that you observe, there is going to be an equal probability, right? And again, I think even without this whole derivation, if you understand this capital F of X in terms of percentile, you could have guessed in a way that, this is uniform distribution. Because see, the number of small x's, the number of variables of x's that you will observe in, let's say, the first quarter of this thing right here will be the same as you observe in any subsequent quarter. So maybe to show that I can draw a little graph where I can show you guys how do we transform, let's say, a uniform. And so how do I transform numbers which are uniformly distributed into normally distributed and vice versa? So again, of course, I will have to have a normal distribution like something on the x-axis, and I'm transforming these into something which is like, which is uniformly distributed. So it will be, I'm just going to draw it something like this for now and not going to make sections. So I'm writing that this is uniform and here we have normal. Okay. Yeah. And the transformation would look something. So again, remember what I have drawn here is nothing that you guys do not know of. So remember what I used to draw always is something like x here and then f of x here, right? But now what is my x? My x is my f of x. And what is my f of x of f of x? Uniform, because we just saw that my f of x follows uniform distribution, right? So this uniform is nothing but the CDF of f of x. So remember how we draw CDFs? We draw it something like this, right? And now what I'm going to show you guys is, just bear with me for a while. What I'm going to do is, yeah. So what I have done is, I have taken the values of x that appeared the most and tried to map them to this uniform distribution right here, right? So if you see this blue line within this orange interval, you see that it is much, much steeper, right? Where you are likely to observe more values of this x. So you observe more values of for these particular x guys, right? Which are the same as these guys. And these, that is why, so you started off with something which is only this wide, but when you apply the transformation capital F, which is basically uniform here, you get something which is much wider than what you started off with because of the number of frequency of the observations here. And similarly, if you do something for these guys here, let's say if you start off here, you end up somewhere there. And again, if you let me start here, oops, this is such a two interval, right? So we started off again with something which is much wider, as at least equally wider as this. Maybe not the same in this case, but yeah, consider this is equally wider. But what you see here, this transformation has clearly taken into account that these observations are not much more observed, right? So the interval really spreads, it really spreads out wider over here and shrinks a bit over here. So the effect is inverse. Whenever your f of x is flatter, you observe less potential outcomes of the random variable x guy here. And again, this happens only because u is the distribution of f of x. U is the random variable which follows uniform 0, 1. So I think this was just, to give you guys some graphical intuition about how we transform basically. So again, whenever you, okay, maybe just let me write. So this blue here is what? It is u, right? This blue here is the function u that you apply to the values here of f of x, which are small u, to get to the point where this u, which is basically, so this is not the u random variable, but yeah, I have written uniform, right? So this is uniform. And again, as we know, it takes only values between 0 to 1. So it does satisfy, right? what we saw was that this CDF only takes values from 0 to 1. So this CDF of this CDF also takes values between 0 to 1 because ultimately it is a CDF, right? And again, what you observe here is that if I give you some random numbers here between 0 and 1, you can always use this U here to give me back the numbers in terms of, numbers. So here the numbers span from 0 to 1, but here the numbers could ideally span from 0 to infinity, right? So for every corresponding value here, you can give me another corresponding value between 0 and infinity, which will follow a normal distribution using this U inverse, because you're coming from y-axis to the x-axis. And if I give you guys some data set which follows normal distribution, you can always use the CDF U and convert it to give me numbers between 0 and 1 with the same properties. Does this make some sense at least to you guys? Yes.
Yes, ma'am.
Okay. So again, the very fact that this CDF follows uniform distribution with 0, 1 is actually, there's a name in statistics for these kind of transformation, and it is known as probability integral transformation. So let me maybe just write it here. So this basically allows you to write your F inverse of XU. And again, when I'm talking that, my probability that my X is less than or equal to this guy, I know that this guy is nothing but small x. So what I've done is essentially just replaced this X with this guy right here. Okay, nothing much new, but just another way of looking at the same concept that we were looking at up until now. Okay, so again, remember, there are two random variables that we now looked at. One was capital X and the other was U, right? And if you inverse this U, you do get back. So let's say if you apply F inverse to this U guy here, so if you apply F inverse to this U guy here, you do get back your X that you started off with, because U is just the value of capital F of X here. So I guess that is clear to everyone. But again, these were just, two different separate diagrams to make you guys understand how can we transform numbers from distributions, from any kind of distribution to uniform. So again, remember here I have given you guys an example of normal distribution. Let's say if we would have a beta distribution. So beta distribution will take higher values here and very low values here, right? So the graph would be something like this right there. And for different kind of distributions, this CDF will look different. But basically it will start here and it will end there for sure, because it has to start from 0 and it has to end at 1 always. And for every other value of X, this is just going to be 1, because the marginals over there will be 0 for the value that this X does not ever take. So I think that was something just about necessary for you guys to understand before we try to actually understand what Copula is. But again, coming back to, yes.
So about the shape of the graph that you had just drawn. So first, like the shape is like that because first the normal distribution, like it is increasing at an increasing rate, and then it is increasing at a decreasing rate, right?
It is decreasing at an increasing, yeah. I mean, first it increases and then it decreases, right?
No, ma'am, the CDF will still keep on increasing, right? Like in the
Okay, we're talking about
latter
the
part,
period.
so you are
Okay, yeah.
adding on more stuff, but that is like lesser than before.
Yes, yes. I mean, the frequency of observing those higher values of X is very less. So whenever you are trying to, basically figure out the chance of that particular thing happening, it's going to be less likely. I mean, that is what you have to capture, right? You have to capture the essence of data, which is how much likely are what values. And that is what you
Ma'am,
project
and
upon.
like the CDF will follow uniform distribution only in case of normal.
No, in any case, right? Because, okay, so when that was a good question. So here we didn't necessarily specify what is my f of x, right? So for any distribution f, but again, thank you very much, Isha, for asking this question. So I forgot to mention that this f here, so there are some certain assumptions that we have to assume for this f to, be able to take its inverse. So the very first assumption is that it should be a continuous line. And this is the only assumption that is sufficient, but necessary condition, this is a necessary condition that f should be a continuous function, okay? So f is a continuous function because only if it is a continuous function, you can take its inverse and its inverse will be defined for every point. Otherwise, it won't be. And for our cases, we are assuming that f is also a continuous distribution. So yeah, because for discrete distributions, you can't necessarily always take the inverse, and it's just, and it may not even be uniform always. So yeah, we are assuming that for every continuous, it's a fact that every continuous distribution f of x, that f of x follows uniform distribution over 0, 1. And thank you very much for asking that question, Isha. Anything else?
No, ma'am, thank you.
You're welcome. What about others? So I mean, for me as well, it didn't really come this easy that I just saw it once and yeah, oh, I know what it means. But again, this will take some time, but you just have to understand what is the essence. So let us say that, I give you some random numbers between 0 and 1, and I tell you that, and I tell you something about the dependency structure. Okay. And what I want to do is I want to basically get it back to get it to a variable which follows normal distribution. So I can use this PDF of or this PDF of the normal distribution and apply inverse transformations so that I can convert some values which are in zeros and ones into some numbers which span between 0 and infinity, and vice versa as well. But again, this is where Copula comes into picture, right? Because how will you do this? Like, it seems really easy in the graph, take x-axis and y-axis, y to x. But again, how do you do this in actual terms? That is what I'll be explaining it to you guys now. And these two graphs will form a part of a cycle that I'm going to draw and in some time. So previous to that, I guess, yeah. I don't know. Okay, so all right. Yeah, I was back.
Ma'am, you're not audible.
So actually what I had to do was, because in my phone I don't have my login, I left my laptop at home, and I guess someone's playing with that laptop now. Okay, so just let me know, okay, if I'm not audible anymore. All right, so what I'm gonna do here, yeah. So what I have here is a lower tail here and an upper tail here, right? So what I was saying is that because I'm plotting on x-axis the payment by the Isha, the money that she pays to me here back, I get in lower tail the chance that she will default, and lower tail is what I'm worried about, right? So remember, in the extreme value scenario, what we were worried about the most was the right tail, right? It was the right tail. That is where the loss would be maximum. And again here, what we are worrying about is the lower tail. So this is the lower tail, and that would be your upper tail. Okay. So now again, if I'm talking about tail dependence, so of course there can be two kinds of tail dependence. One, upper tail dependence. Second, lower tail dependence. So as we just saw, upper tail dependence would be something. So let me just maybe write it down. So we denote upper tail dependence by lambda u. And again, this is true asymptotically. So I'm going to take limits. But again, we'll see what do I take limits of. But I'm looking at the probability that I observe my value of x greater than some x, given that I've observed my value of y greater than some small y. Okay, so I haven't really specified the limit as yet because we are going to change certain terms here. So from what we saw previously, how can I rewrite my small x as? I can rewrite my small x as something which is fx inverse of u here, right? So what I'm going to do is I'm just going to substitute instead of that small x, f inverse of u here. So remember, this is just my small x, right? This is just another way I can write my small x. Because what is u? U is just the value that my f of x takes here. And if I apply f inverse to it, I will get back my small x. So again, I can replace easily my small x with x inverse u. Is this clear to everyone? Does this make sense? If I rewrite probability of x greater than x in such a manner? Yes or no?
And can you please repeat it for once?
Okay, yeah, all right. So, okay, what I do normally is, so if I have something like this, I know that my f of x is 1. It is just the probability that my capital X takes a value less than or equal to small x. And I'm saying that its value is small u here, right? So what I can write here is, I can just change this. I can apply f inverse in both the sides. And what I get is f inverse u is equal to small x. And now what I do is, instead of writing a small x here, I replace this small x with f inverse u. Does this make some sense now?
Yes, ma'am. Got it.
So this f inverse u is what I have here. And I've essentially replaced this x with this x, this x, this x here. Right? So this is essentially the same thing. Any more doubts? Anyone? So this is the only difficult thing in this chapter, I would say, to understand this transformation, to understand what exactly is happening here. And I hope these diagrams are making understanding a bit better for you guys, at least for now. So again, what I'm going to do now is write my y as well. So what I will do is I will write my y again. Similarly, the way I rewrote my x. So I'm going to write my y greater than f inverse more than. And now I'm going to take limits where I approach u from below. So again, remember, whenever I'm defining my small u is what? It is f of x, right? So it only takes values between 0 and 1 as any cumulative distribution function would, right? So my u only takes values between 0 and 1, which is why, so again, I mean, these are the values of u, right? So I can write that this is capital U that I have plotted here, of which this small u are the values, right? And these can at max take the value 1. So what I'm saying essentially is that I'm approaching this limit of 1 from below. So whenever I write 1 minus means I'm approaching this limit of 1 from below, not from above, because I mean, you can't necessarily just do anything up there. You have to approach it from below. So I'm saying in limits, so asymptotically, because again, remember, what are we looking at? We're looking at upper tail dependence, right? And whenever I'm talking about upper tail dependence, what I care about is this area right here, right? So my u has to go as high as it can possibly, which is in theory 1. Does this make sense? So again, now, if you have a look at the previous measure, so you studied about rho, Pearson's rho, Spearman's rho, Kendall's star, or let's say Rolf's rank correlation itself, they will all be between the value of 0, between the value of -1 and 1, right? But here, whenever you're talking about the upper tail dependence, so this lambda u here is the coefficient of upper tail dependence, okay? And this is what? This is the limit. Okay, so you don't take this into consideration, you take this into consideration. This is a limit for my u guy here. And for some probability, right? So we are talking what happens to this probability in limit. But again, I know that my probability can only take values between 0 and 1. So again, this coefficient of upper tail dependence, which is lambda u, will only take values between 0 and 1. Because we're talking about a probability here. And again, as it would be in any other case, if your lambda u takes a value 0, then you say that x and y are asymptotically independent in the upper tail region. Because remember, this is not any tail dependence, this is only the upper tail dependence that we're talking about. So we are talking only about the upper tail dependence, okay? Which is this area right here. So again, similarly, you can also talk about lower tail dependence.
Ma'am, over there for u, you have written u tends to what?
1 minus. Maybe I can write that a bit clearer. So it is 1 minus. This is 1 minus.
Can you just explain again why 1 minus?
Why 1 minus? Okay. So because we are looking at upper tail dependence, so this comes here because we are looking at upper tail dependence, right? So whenever I'm looking at upper tail dependence, what value of u you are likely to have? Near about 1, right? because U takes values from 0 to 1. I mean, what is small u? It is the value of my CDF, which takes values only from 0 to 1. And whenever I'm talking about upper tail dependence, I'm basically talking about when my Isha also pays me the money and Anvaya also pays the money. So that happens here, right? So both of my loans will be repaid. And that is what happens here in the upper tail. And whenever I want to care about this, and because I have written U here for both of these guys, X and Y, I know that this is also, I mean, so again, remember this graph I have drawn only for X, okay? I haven't drawn for Y. So I will draw the next graph, which would be about both X and Y, where you will have like a different value for X and a different value for Y, not necessarily U. I take a U and a V there, but here I'm assuming that it takes the same U, and that is why my U only cares about, when I approach one from below. So I'm approaching this one guy here because I take, okay, ideally I should
But why the minus sign?
because I'm approaching it from below Isha. So see, what happens is if I would write a plus there, what would I be doing? Or if I let's say write nothing, then what's happening is essentially I can approach one in limit from here as well as from here, right? But if I know that my U won't take any values above 1, so to specify that we are approaching 1 from below here, but starting from here and we are going upwards, so we are approaching 1 from below. So even I find this notation a bit counterintuitive, but now I'm used to it. So I can easily see that if I'm writing 1 minus, minus means I'm approaching something from below. Does this make some sense now?
Got it. Yeah.
Got it? Perfect. Thank you very much for asking. I guess that must have clarified this again for everyone, I guess. Does this make sense to everyone?
Yes, ma'am.
Okay, so now it is up to you guys to decide what limit will there be for my lower tail dependence. So again, I'm going to have U tending to something. And here I'll have probability that I observe as X less than F inverse U, given that my Y is less than F inverse U. So again, I'm just looking at what is the probability that Isha will default given that Anvaya has already defaulted, right? This is what I care about, lower tail dependence. So what should I write here for limit? So again, whenever I'm talking about lower tail dependence, I'm looking at something here, right? And what value it is approaching here and from where? Will it be from above or will it be from below?
Will it be 0 plus?
Exactly, it will be 0 plus because our U at the end takes value 0 and you cannot necessarily approach it from minus. You have to approach 0 from above. So you are taking into not only the exact 0 into account, but something here as well. So this square is what you are taking into account for lower tail dependence. Does this make sense to everyone? And again, this would also take values only between 0 and 1. So please let me know now if you haven't understood any of what we have studied up until now, so that I can revise it again, and then only I will go forward to draw the diagram that my professor drew, back in London. Any doubts so far? So again, remember, what is Copula even trying to do? It is trying to basically, figure out the likelihood of a default if there is a correlation between the variables that you are looking at. All right. So it in a way, looks at the implicit dependency that might not be captured otherwise in the normal correlation measures that we have had a look at as yet. So again, during the times of financial crisis, there was liquidity risk as well. Companies didn't have enough liquidity, and that is why they ran out of cash, and their loans to the housing and the mortgages, they went bad. And basically, I guess if you want to understand the crisis better, you can watch the movie The Big Short, or else I think I will just link up a video from YouTube, which I know is the best to explain what exactly led to the financial crisis. But again, I'm not even sure if they see the word Copula even once throughout the video, but you guys would know the actual secret, right? So I guess there's a Wall Street Journal article as well, which titles Recipe of the Disaster. And I'll also link up that article if anyone wants to read. And that would be, I guess, in the dinner soup area, which is optional if you prefer. So again, now I guess, any doubts, anyone so far? So we studied the two usual measure of dependence, and what we observed in Pearson is that it is not necessarily invariant to increasing transformations on the random variables. So rank correlations do away with that con of the Pearson's rule, and these are essentially invariant because of the fact that they only care about the rank and not the actual number. And the ranks do remain constant if you uniformly transform all the random variables using the same function. And again, then we had a look at how we care about the lower tail and the upper tail. So again, if I'm looking at the payment, I care about the lower tail the most. And if I'm looking at the default, I'll care about the maximum default that these both people will do, which would be right up there in the upper tail. But again, we have to be sure if these are independent in normal terms, or if there any implied association or dependency that we might be missing out on. And then we had a look at a concept which is defined as probability integral transform, which will allow you to essentially take random numbers and keep the dependency structure as it is, but transforming those numbers and having a corresponding number for each of those, which lies only between 0 and 1. And again, you can take some values which are 0 and 1, and you can force upon the dependency structure that you see somewhere else to get you to a distribution which will also have the same dependency structure, but values between 0 and infinity. And again, then we had a look at the coefficient of upper tail dependence and the coefficient of lower tail dependence, which is lambda q and lambda l respectively. Okay, so now we'll have a look at Copula. We have only yet studied what drives, what drove the introduction of Copula and what led to even, the discovery of this Copula. So I guess, this Gumbel Copula is something that we'll be studying in the upcoming lectures, and there's a very interesting story about this Gumbel guy and how he discovered and stumbled across the Copula, which is now known as Gumbel Copula, and which was in a way responsible, whose misuse was, its misuse was basically responsible for the financial crisis of 7-8. So again, coming back to the crux of this whole chapter, let me draw first some. So remember, up until now, what I have drawn is x on the x-axis and f of x on the y-axis, right? So now remember, what I'm drawing is x on the x-axis and y on the y-axis. So this is the first time I'm doing this. I mean, apart from the time when I had repayment of Isha and repayment of Anvaya here. So this is now I'm writing x, y. And what I'm going to have here is, so let us say I have observed something here, in which I will call x, y. So this is the coordinate x, y that I have observed. Okay, and so I'll have a certain respective value of x and a certain respective. And a certain value for y. Yeah, so I guess, yeah, it's fine. So actually the battery of my phone is very low. I mean, the phone that I'm using right now is just, the Kaam Chala wala phone, and it doesn't really support well. But again, its battery is low, so I may cut off any time. But yeah, I'm just trying to explain at least this diagram before I cut off. Okay, so I have this x and y coordinates plotted on this x and y area here. Okay, and what I can do is I can draw simultaneously here for my x guy. Hello, am I audible now?
Yes, ma'am.
Yes, ma'am.
I guess let's just conclude our lecture today here itself, because my phone's battery is critical and it can die anytime soon. So I guess that's all for today, and we'll do this diagram in the next lecture in the next class, which will be a day after today. So today is Tuesday, and we'll take the lecture on Thursday. Okay, and I will probably take a lecture for 2.5 hours. That, if that is all right with each of you. So I guess we'll have a lecture from 4 till 6:30 or something. Does that work with everyone?
Yes, ma'am.
All
Yes,
right.
ma'am.
Yes, ma'am.
Good. So just try to revise what we have done up until now, and I guess maybe what I can do is take next lecture for 2 hours and the lecture after that for 2.5 hours, because then you would have even a better understanding. So we'll have a look at how much I cover in that lecture. But again, just keep your half an hours free for the next 2 lectures, apart from the 2 hours that I'll ask you guys of. Okay, then just let me know if you have any doubts. You can either SMS me, but again, the network area in my area is also not really good. So emailing is probably the best way to do. But yeah, I guess that's it. I can't even install WhatsApp on the phone that I'm using right now.
Ma'am, from next week we'll have regular lectures on Monday, Wednesday, Friday, right?
Yes, yes. I intend to do that. So actually, I'm also doing a bit of research work, and we had a deadline, so I had to rush up a bit sometime, and then there were some issues as well other times. So